Okay, the solar system. So as I'm going through this is an exciting time. We're looking at why the solar system is set up the way it is, and I think it's pretty self-explanatory. So our objectives are we're going to compare the models of the universe developed by Ptolemy and Copernicus. That's something you should be able to do, and then summarize Kepler's 3 laws of planetary motion. First of all, as far as the models of the solar system, if we start some 2,000 years ago, the basic school of thought is what we refer to as a geocentric model. In other words, geo meaning Earth, centric meaning Earth-centered. And this was proposed by Aristotle. And basically, we were very egocentric back then. We thought about ourselves and everything was about us. And so the Earth was the center of everything, and they felt that everything in the sky moved around the Earth. Now, the problem was, and as we looked at this earlier, the problem was it looked like the planets were doing giant burnouts in the sky. And they were doing giant circles and going round and round. And I've got a real good visual of this, and I think you'll see it. So as this moves around, you can see that if the Earth was a center of the universe as proposed, that it appeared as if we were to draw these out, that these planets were all doing giant donuts out there. Probably a pretty cool design for a tattoo, but still not correct. It is not a model that is correct, but it's a pretty design. So from there, we started to try and put things together, and we refer to that going back and forth as retrograde motion. The giant circles that the planets were doing, they referred to as epicycles, and so Aristotle and Ptolemy basically said that since we're at the center, everything's going around in circles, and we see them going around the Earth. And again, retrograde motion would explain what they saw. So as we see Mars, Earth is changing its position, so it appears to go back and forth as we go around because Mars has a greater distance to travel. Then comes along a guy by the name of Copernicus. Now, this is in the 1500s, and so we're talking about an era of knights in shining armor and things like that. Well, Copernicus comes along and says, listen, guys, the reality is this. Earth is not the center. According to my model, the sun is. And so the Earth and the other planets are going around the sun. And so as he proposed this was a very dangerous thing, right? This was something that could get him killed. And he proposes this and explains that he believes that instead of them doing giant burnouts in the sky, they're actually all going around the sun. In fact, they're all going around the sun and going around the sun in the same direction. And that was his explanation for everything. Well, sure enough, a lot of people didn't like what he had to say, but they were listening. And along comes a guy by the name of Galileo Galilei in the 1600s, and he has this newfangled invention. It's called the telescope. And by doing that, he actually proved Copernicus was correct in that the sun was at the center of the universe. Now, other people did some incredible work during this time too. Tycho Brahe, Kepler, these guys were mathematicians. Well, math is the language of science, right? And so what were they doing? They were trying to prove the path that Copernicus was talking about, and so they wanted to do it in mathematics. And so the first law, Kepler's law, is that planets orbit the sun in an ellipse. An ellipse is an oval, and basically an oval is a circle that has two focuses, right? And as we've talked before, aphelion and perihelion. Aphelion is away, and perihelion is when the orbit is closest to the sun, to a point. So we talked about this with satellites. The distance from Earth to the sun is called an astronomical unit, 93 million miles. Why do we do this? Because there's a lot of big distances out there, and so we wanted to make it to where it was a user-friendly number. Instead of saying, oh, it's 48 trillion, 547 billion, 600 whatever miles, we said, oh, it's just 1 AU, 1 astronomical unit. The second law of Kepler was that the law of equal areas. It said Earth moves fastest when it's close to the sun, and it moves slower when it's further away. Okay. Now, what that means is, as we're coming closer, we're slingshotting around. Okay, get that. And this comes through to his third law, the equal areas in equal periods of time, or the relationship in the orbit time. Basically, what it means is the radius of the orbit cubed equals the period square. So I think it's easier to show you what I'm talking about, and I think you'll see it. So this is the diagram, which I really like. And so basically, as Earth goes around the sun this way, the time it takes to go from this dot to this dot, or from this dot to this dot, or this one to this one, or this one to this one, etc., is equal. This is equal areas and equal times. And the area of the triangles are all equal. Now, granted, what's happening? Earth is slingshotting around. It's getting at the very edge of the gravity, and it pulls it back in, and it speeds around. So let's do this from start to finish. So again, Earth is traveling around, and as it gets further out there, it's slowing down a little bit, and so the distance it's traveling between dots while it's the same time is slower, right? But these are equal areas. Perfect example of Kepler's third law, third and second law. And then Newton comes along. Now, here's the beauty about Newton. Newton takes Kepler's law, and he wants to keep things going. So he hypothesizes that basically a body in motion will only change if there's an outside force acted on it. So in other words, a ball that has no friction or anything else will keep going in outer space unless something hits it, right? Well, we now know that force, as it moves in a straight line, it has a tendency to move in a straight line, is called inertia. And so from that inertia, then we also know Newton then ends up identifying what gravity is. And we now know that it wasn't an apple that fell on Newton's head. It was the fact that he saw a comet travel around the outside of the sun, and it was that relationship of Kepler's work that allowed him to figure out what gravity was. So great job today. You know, what was our goal? Our goal was to be able to compare the models developed by Ptolemy and Copernicus, and then summarize Kepler's 3 laws of planetary motion. So great job. I'm excited about where we're at, and we'll catch you on the next one.